Now we'll talk about the crystal structure of the semiconductors. So let's talk about the states of a solid. Why does it matter? So when you have the flow of charges through a solid, it strongly depends on the arrangement of atoms, how they are arranged. Okay? So solids can be classified into three states depending upon the arrangement of atoms. So you have the crystalline solid, in which you have periodic arrangement of atom, a regular arrangement, very well-defined arrangement of atoms. Then you have amorphous, which do not have any arrangement, right? No arrangement of atoms. And then you have polycrystalline solids, which have arrangement of atoms but only in a certain region. And you have several such regions which may have a different arrangement of atoms, but you can't say throughout it has a same arrangement of atoms, right? So that's a polycrystalline. Okay, so so periodic order, if you look at the periodic order, largest is here, no periodic order, some periodic order, right? If you talk about the transport of charge, it will be much smoother in a crystalline solid, amorphous, not good at all, and polycrystalline somewhere in between. Okay, so that's why it is very important so that we generate these crystalline materials, especially when we talk about the transport. But polycrystalline and amorphous, these materials also exist, right? They have their own applications, but we'll start with the simplest one, crystalline. Okay, so crystalline solid is what I'm going to focus from now onwards, and unless I specify otherwise, we'll assume that it's going to be crystalline solid. Okay. Okay, so if I talk about a crystal lattice, so lattice means, what is the meaning of the lattice? So periodicity of the crystal can be defined in terms of the lattice. So basically lattice is a periodic array of points. Okay, so periodic array of points in 1 dimension, in 2 dimension, or in 3 dimension, whichever is your crystal, I mean whatever your system is, you can arrange the points in 1D, 2D or 3D. So that's called crystal lattice, that array of a periodic array of points. Now there is a special class of crystals which is called Bravais lattice. So what is Bravais lattice? There are two equivalent definitions of the Bravais lattice. So let's talk about the first definition. So first is, so it is an infinite array of points formed in such a way that the orientation remains the same no matter from which point you observe it. I have a arrangement of points, and no matter at which point I sit and look around, I will find exactly the same arrangement as at any other point. Okay, so it's like, for example, you have say chairs here, right? And there's a perfect symmetric arrangement of chairs. No matter if this room is say big enough, very big room, and you have perfect periodic arrangement of these chairs, no matter at which chair you sit, you will find there is the same arrangement of chair around you everywhere. Okay, so that's a Bravais lattice. So that's the definition one. So for example, I have say this arrangement of points. Assume that this is infinite. I mean, I have drawn it in a finite manner, but assume that this is infinity here, infinity here, infinity here, right? Now, no matter at what point I will sit. So if I sit at say this point, I see an atom in this direction, this direction, this direction, this direction, right? So this is an arrangement of atom. If I sit at say this point, I see a similar arrangement of atom. I mean not atoms, the points. Okay, the points around the same. Okay, so you can choose any point. So arrangement does not change. So that type of lattice is called Bravais lattice. Not just the arrangement, the orientation of the points should also remain the same. Okay, I'll give you an example which is not a Bravais lattice later on, and you will see that arrangement looks the same, but the orientation is not the same. So that is a lattice, but not a Bravais lattice. So if you have a Bravais lattice, then it can have another equivalent definition which is more mathematical. If you have such an arrangement that from any point if you look it remains the same, then in that case it will consist of all the points in the space with the position vectors of this form. Position vector of any lattice point in that lattice will be given by this form n1 a1, n2 a2, n3 a3. n1, n2 and n3 are integers. a1, a2, a3 are any three vectors not in the same plane. Okay, and they are called primitive vectors or basis vectors. Okay, so any point in this lattice I can express the position vector of that point in this form: n1 a1 plus n2 a2 plus n3 a3. a1 a2 a3 is the basis vector or the primitive vector. Now let me give you an example, the same 2D example that we saw. So in this arrangement of atoms, a1 and a2 are primitive vectors. Now if I take any point in this, I can simply express the position vector of that point in the form of a1 and a2. Okay, and the coefficients will be integers. I can take an algebraic sum of the combination of a1 and a2, integral multiple of a1 and integral multiple of a2, and I can combine them, add or subtract them, and I will be able to create every point. Let's take an example. Say point P and Q. Okay, so what is the position vector of the point P? Assume that this is the origin. So what will be the position vector of the P in terms of a1 and a2? So a1 plus 2a2, right? We are doing the vector sum, and similarly Q will be minus a1 plus a2. Similarly, any other point can be expressed in the terms of a1 and a2. So a1 and a2 are the basis vectors or the primitive vectors, and I can do some combination of those, integral combination, and I can generate the whole lattice. So this is the 2D example. Let's take a 3D example. So this is a simple cubic lattice. So simple cubic lattice means it's a cubic lattice, 3D, right? Because it's a cubic, so all the three sides have the same magnitude. This side, and this side are equal. Okay, so a1, a2 and a3, these are three primitive vectors here, and they have an equal length. Okay, a1, a2, a3 equal length, and this is going to be a simple cubic lattice. So simple cubic lattice is a lattice in which you have the lattice point only at the corners. See, so there is nothing inside, but at the corners you have the lattice point. Okay, and a1, a2 and a3 in this case are mutually perpendicular primitive vectors. So now let's talk about a non-Bravais lattice. So why it is a non-Bravais lattice? So a honeycomb structure, for example, graphene I was talking about. Graphene has this honeycomb structure. It is definitely a lattice. So lattice is something in which you have periodic arrangement of points. Definitely there is a periodic arrangement of points. If I keep repeating this thing, I will be able to create a whole periodic arrangement of the full honeycomb lattice. Yes? But this is not a Bravais lattice. Why? Look at, say, point R and look at point Q. So if I sit at the point R and look around, what do I find? I find that in this direction I see 1 point, 1 point, 1 point. And if I sit at point Q, what do I see? I see a similar arrangement of atom. I see again 3 points here, here, here. But what about the orientation? It's 180 degree. You know, when I sit at R, I don't see any point in this direction. I see a point in this direction. But in this case, I see this point in the opposite direction. Okay, so it's like a 180 degree rotated arrangement. It's not a Bravais lattice. So you have similar arrangement, but not exactly the same. It's a lattice, but not a Bravais lattice. Okay, so you won't be able to apply the Bravais lattice, you know, position vector equal to n1 a1 n2 a2 n3 a3 in this case. Now we talked about the primitive vectors a little bit, right? So primitive vector is something from which I can create any other vector in the lattice from its combination. It's like a unit vector. Yes, in your normal coordinate system x, y, z, you have x cap, y cap, z cap, right? Or I cap, j cap, k cap, whatever you want to call it. So these are unit vectors along 3 perpendicular directions, right? And you can generate any point in the space in the form of these unit vectors. Yes, so primitive vectors are the same. The only difference is that you are not talking about any point in the space. You are only talking about the lattice points. Okay, so you must be able to generate the lattice points. Now the set of these primitive vectors it's a non-unique set. So it could be that there are several possible primitive vectors for the same lattice. It's non-unique. For example, for this lattice that we saw, we talked about these two, A1, A2. Yes, so these are primitive vectors because I can express any point in the form of these two. But this and this, these are also primitive vectors. Now just think about it. If I have to say express the coordinates of any point, I will be able to express as a combination of these two. I mean, it's the simpler one. Let's look at a more complicated one. This is also a primitive vector. This and this. Okay. In fact, this and this is also a primitive vector. So how do we then generate the primitive vectors? Right. So one thing is that, okay, you just draw some set and you then check several points. Are you able to express in terms of these primitive vectors or not? But that exercise is like, you can't keep doing that. So is there a way I can say that if I'm drawing two vectors, they will be primitive vectors or not? Okay, so there is a geometric way of doing it, right? There is a whole algorithm. We won't go into the detail, but I will tell you a more easier way. So what you can do, you sit at one point, okay, and you look at the neighboring points, so the nearest ones, right, and just draw some lines. Say this and this, okay. So this is the most easier set of primitive vector I can find. So once I find this set, let me draw an area formed by these two vectors. So area formed by two vectors will be what? So this vector and this vector will form this area, right? This parallelogram. Yes? Mathematically it will be given by A1 cross A2, the cross product of the two. Okay, if you are not familiar, fine. But this parallelogram that you see, this is the area formed by these primitive vector. One easy set of primitive vector you can always find. Okay. Now this area, there is a property that the area formed by the primitive vectors will be the same for any set of primitive vectors. It will remain the same. So once you find this area, now you know this number. So this must be this area. Now any other primitive set of vectors that you find, they must have the same area. If they don't have the same area, they will not be primitive vectors. For example, this and this, they are also primitive vectors. If you look at the area formed, this area and this area, if you do some mathematical calculation, you will find that these areas are the same. Okay, so what you have to do, you will have to sit at one point and look in the 2D in two directions in which you will find a lattice point. Okay, now if I look in this direction, the first lattice point I find will be this. If I look in this direction, the first lattice point I find will be this. So yes, these two are primitive vectors, and then I will do my area calculation, and we'll see if it is matching or not. Then say I can look in some other direction also. I go in this direction, the first lattice point I find is this, and then I go say in this direction, the first lattice point I find is this, right? So these two vectors are potential set of primitive vectors. I'm not sure they are primitive vector or not. So what then I will do? I will do then the area test. Okay. So it must pass the area test also. Area must remain the same. Okay. So all of these, if you see the area found by these, it will remain the same. Okay. So the set of primitive vectors it's a non-unique set. So this is a very simple 2D example. Now let's look at some real useful examples of the primitive vectors, which will be useful for us later on. Primitive vectors of a body-centered cell. So what is a body-centered cell? So body-centered cell looks like this. So it's a repetition of this type of arrangement of atoms. So you keep repeating this arrangement of points, you will generate a body-centered cell. Okay, or a BCC. So you have a simple cubic. This is a simple cubic lattice, but inside, in the middle, exactly in the middle, you have one more lattice point. So that's called BCC. Now what will be the primitive vectors for the BCC? You know the primitive vectors for the simple cubic, which is A1, A2 and A3, right, along these three sides. But what will be the primitive vectors of a body-centered cell? Again, there can be infinite possible sets. So how do you do how do you generate at least one primitive primitive vectors, one set of primitive vectors? So again, I will look in some directions, right? The first lattice point I will find, I will note that down, the coordinates of that, and from which I can generate my vector, right? 3 vectors I can generate, and then I will do the volume test here, not the area test, the volume test. Now how do I find the volume of one primitive cell? Can you tell me? Just looking at this. So the area formed by the primitive vectors, if I repeat that, that is going to generate the whole lattice. Look at this. If I keep repeating this thing, this is just one patch. If I keep putting these patches together, I will be able to generate this whole geometry. So the minimum volume, minimum repeating area is this patch. Yes. In this case, I know that this volume is repeating. Okay, but is this thing is the minimum repeating volume? Again, let's go back. This minimum repeating area has one more property. How many number of points are there in this repeating volume? How many points are there? 4. How many points are there in this area? 1. It's just 1 point. This point is shared by 4 others. So, this. So this is going to keep repeating like this. So this and this. So all of them. So 1 point will be shared by 4 parallelograms. So in total, the contribution of 1 point is just 1 by 4, right? So one smallest volume has 1 point. So this is again a property. The repeating volume, the smallest volume will be the one which will have only 1 point. What about this? How many points does it have? 2 points. How? So contribution of the corner point is 1 by 8. Think in terms of 3D, right? So this is not just one cell. There will be surrounding cell. It's a whole crystal. And if you look at this point, it will be shared by 8 other neighboring cells, right? One here, top, bottom. You can generate the whole. You can just think about it. Right, there was that simple cubic lattice that I showed, so you will probably able to appreciate from that picture more. So it has 2 points now. Okay, so the volume which has 2 points is this. What will be the volume which will have only 1 point? What is the volume of this? A cube. A, right? And this volume contains 2 points. So what will be the volume? So there exists a volume, it means, which has only 1 point, but we don't know what is the shape of that. But we can calculate the volume of that. That will be A cube by 2, right? 2 points have A cube, so 1 point will have A cube by 2. So now I know the volume of that repeating cell. Okay, let me do the same procedure that I used to follow. I will look in 3 directions. They should not be parallel directions, of course, right? You won't be able to generate anything otherwise. So they should be known coplanar vectors, right? A1, A2, A3, known coplanar, known linear. So let me look in this direction. This direction. So this direction, if I look, I find this point. If I look in this direction, I find this point, the nearest one, right? You will find more points later on, but the minimum distance is this. And let me say, look at here in this direction. So I encounter this point. Now let me check whether these 3 guys, these 3 vectors, form a set of primitive vectors or not. Let's write down their positions, right? So assume that this is the origin. What will be this vector, and this vector? Can you calculate? So this vector, and this vector. Assume that this is x, this is y, this is z. What will be the position vector of this? So this is x, say this is y, and this is z. What will be the position vector of this? What is this vector? It's easy one. So this is a y cap, right? What is this? A x cap. What about this? This vector? So to reach the middle, you will go half here, half here, half here. So a by 2 x cap plus y cap plus j cap. Got it? So these are 3 vectors. Now to determine whether it's a set of primitive vectors or not, what should I do? I will have to create the volume formed by these 3 vectors. Now what will be that volume? Can you imagine? What will be that volume which is formed by A1, A2 and A3? It will be a little complicated. I'll show you the picture later. But the volume created by the 3 vectors, it will be a parallelly piped. So there is a parallelogram. The 3D version of that is parallelly piped, right? So the volume of the parallelly piped is this. So A1 dot A2 cross A3. A1 dot product of A2 cross A3. And if you actually do this, it's not a very difficult calculation. A2 cross A3 you can very easily find out, right? It's simply X and Y. You know, X cross Y gives you Z, Y cross Z gives you X, so all of that. So if you do that, you will find that the volume is actually A cube by 2. You can do that exercise at home. So this is a set of primitive vectors, right? Now let's do some coordinate check, whether we are able to generate the position vector of every point in the space with the help of A1, A2 and A3. Let's see that. So let me try to write this P in terms of A1, A2 and A3. Can I write the position vector of the P in terms of A1, A2 and A3? So what is the position vector of the P in terms of, say, Z? So this is A, so this is A Z cap. Can I write A Z cap in terms of A1, A2 and A3? Yes, I can. If I multiply 2A3 and then subtract A1 and A2, this term and this term will get cancelled, right? What I will get is simply A Z cap. This is just one example. It looks a little bit complicated, but yeah, it's not something you'll have to do again and again, right? You can simply just remember, oh, A1, A2 and A3 in a BCC look like this, but it's good if you know the logic behind all of these things. Similarly, you can calculate the position vector of, say, point Q here. So this is the point Q. You can express it as A1 plus A2. Okay, so this is one set of primitive vectors for a body-centered cell. Can I find one more set? It looks like it's a little bit complicated, It doesn't look symmetric. A1 and A2 are equal, A3 is something entirely different. Even their directions, if you look at, this and this. So it looks a little bit complicated. If I have to express the coordinate of any point in terms of A1, A2 and A3, it looks a little bit complicated. So do I have another set which is more easier? So BCC have another commonly used more symmetric choice. So what I have done here is, so you saw this cell, right? It has this body centered point and all the other points here. Now let me draw another BCC cell here in front of this and at the bottom of this. So 3 neighboring cells I have drawn. This in front and on the side. Okay. Now from this point I can connect the body center of all of these neighbors. They will also form a primitive set. So from this, the center of this front cell will be here. So there is one vector here, A1. Okay. The center of this another side neighboring cell is here. The center of this another neighboring cell is here. So A1, A2 and A3, they all have the same length and they are more symmetric, right? So this is one more set of primitive vector. You can write the coordinates, not very difficult to write, okay, but one more set. So you will find this set in the books, right? Again, you can express point P, Q, all the points in terms of A1, A2 and A3. Not very difficult. Okay, so let's now look at the primitive vectors of a face-centered cell. So we have covered simple cubic, we have covered body-centered. There is one more very important lattice which is face-centered. So what is a face-centered lattice? Looks like this. So you have a cubic lattice, atoms at the corners of the cube, and then you also have the atom at the center of every face, which is this. For example, this face has this center atom, this face has this center atom, top face has this center atom, right? So this is called face-centered cell or FCC. Primitive vectors, again, you can find, you can start with any 3 direction. I mean, I can do that volume exercise again, calculate the volume, then I will start in these three directions. We'll end up at some coordinates, we'll encounter some point, I will write down their position vector, and then I will check whether their volume is equal to what I calculated in the beginning or not. We can do all of that exercise, but I will just write down the primitive vectors here. So if I am here and I connect the face, the center at the center point of every face. So this face has this center point. So this is one vector. This face has this center point. So this is another vector, and this face has this center point. So this is another vector. So these 3 vectors are also primitive vectors. Okay. So I had 3 adjacent faces, this face, and the bottom one, and I simply connected their center atom to the origin. So that forms these 3 vectors that will be generated. They will form primitive vectors. Coordinates you can calculate. I'm going to skip this mathematics. Of course, there will be no third unit vector here because it's at the face. So one of them will be missing. So if I say look at A3, so there won't be Z there, right? So it's half of X and half of Y. Yes. Similarly, the other 2. So there is one more concept called coordination number. A coordination number is the number of nearest neighbors. If I am at a point in that lattice and I look around, how many nearest neighbors I can find, that is my coordination number. Okay, nearest neighbors means neighbors which are closest to this, right? And obviously because I'm saying neighbors, it means there are several of them and they have equal distance from this point, and the minimum one. So for example, what will be the nearest neighbors in a simple cubic lattice? Number of nearest neighbors. Can you think about it? Always think in terms of the whole lattice, not just one unit, one cell. How many? What, 4, 5, 8, 6? 6. Yeah, so it has 6 neighbors. Why? Say I sit at here, right? So this is equidistance from here, equal, right? A. So 3, right? Similarly, I can draw a same cube on the side. Here I can draw the same cube. So 4, right? And 5 if I draw a cube in the front, and if I draw a cube on the top, 6. So 6. Got it? If you don't get it, then go back to that whole cubic lattice picture, right? So there was this whole lattice I drew somewhere in the beginning. So you can very clearly see from there that there are 6 such points. What about a BCC? How many neighbors? Nearest neighbors. How many nearest neighbors? So this thing is going to repeat. Front, side, top, bottom, everywhere. What? 10? 8. Is it 8? Can you see why it will be 8? Yeah, look from the center. How many points, nearest points you find? 1, 2, 3, 4, 5, 6, 7, 8. I mean, this is the easiest one. Okay, 8 neighbors. Every neighbor has equal distance. What about FCC? 12. Anyone else? Okay, it will have 12. Now think why. 12 neighbors. 12 points which are equal distance to any point in the lattice. Okay, so let me give you, let me draw two FCC cells side by side. So this is one FCC cell. This is another FCC cell. Now I'm going to focus somewhere here. So let me look from this point and let me see how many neighbors it has. I can see 1, 2, 3, 4, and so 2, right? This line will give you two neighbors. 4, so there is a plane. Look at this plane. This distance and this distance are equal distance. So 4 in this, and there is one more plane which is this. Okay, 1, 2, 3, 4. So let's complete this plane first. So 4 plus 2 plus 2, 8, then 10, 12. Got it? So 12 in total. So let's talk about our 2D lattice again. And let me draw an area here. Okay, so these are primitive vectors. Let me draw the area found by the primitive vectors. This. Now if I repeat this area, I will be able to generate this whole lattice. Translate this. So let me translate it like this. Okay, this. So you will be able to fill the whole available space without any gap. So this is called primitive unit cell. And primitive unit cell, as we already figured it out, it only has one lattice point. Yes? Any primitive unit cell will have only one lattice point. And all the primitive unit cells will have the same area. Now, primitive unit cell is also non-unique. As you have the non-uniqueness in the primitive vectors, you have the same non-uniqueness in the primitive unit cells also. It means I can generate different shapes and repeat them. They will be able to generate the whole lattice, but the shapes may not be the same. For example, all of these are possible primitive unit cells. Okay, I can repeat this or repeat this. All of them will have one lattice point. It is not necessary that I need to draw this volume through the lattice points. You can see that there is no lattice point at the corner of this unit cell, but there is a lattice point inside it. So still one unit cell, still one point in total, right? So I can draw it around the point, I can draw it through the point. Whatever I do, in total, it should have one lattice point. I could have done this, okay? Or I can draw it in the surrounding of a point. Different shapes. It doesn't have to be well-defined geometric shape. You can draw arbitrary shapes like this. But it has to be the same shape and it has to be the repeating one. By the way, this area, and if you calculate this, they will have the same area. Okay, so it can have any weird shape, but same area. In 3D, it will have same volume and only one lattice point. Then it is called primitive unit cell. Okay, so how to generate a primitive unit cell? So if you know the primitive vectors, right? So easiest way would be, if you know the primitive vectors, the volume or the area formed by the primitive vectors will always be the primitive unit cell. For example, this, if the area formed by this A1 and A2, that will be the primitive unit cell. Now in 3D, let me draw it. So in case of FCC, this is how my primitive unit cell is going to look like. A very complicated shape. So what were the primitive vectors of FCC? The face center points, right? So this was my A1, okay? So this face, and this is the center, A1, this face, this is the center, A3, and this face, and the center, A2. Now what will be the volume formed by these three vectors? So this, and this. So let me draw a parallelogram here. Okay, and let me extend this in the third direction up to the length of A1, right? So I have this parallelogram and I extended this behind in this direction. So this gray means this is behind. Okay, this means it is at the front, so like this, and you got a shape which is called parallelly piped, 3D version of the parallelogram. If you look numerically its volume, so volume will be equal to A1 dot A2 cross A3 always. But this is a very complicated volume. I want an easier way to draw a primitive unit cell. There is a primitive cell called Wigner-Seitz primitive cell. It's a primitive cell, but a special type of primitive cell. How do we generate it? So this is a primitive cell which utilizes the symmetry of the crystal, and by definition, geometrically, what it is, it's the volume or the area of the space around a lattice point which is closer to that lattice point than any other point. A little bit confusing. Region of space that is closer to that point than any other lattice point. So if you are in this region, you are closer to the given point than if you are outside this region. If you are outside this region, then you are farther. How do we generate that? And whether this definition will be fulfilled, we'll see. So let's first geometrically try to generate it. There is a step-by-step way to do it. How do we do it? So say you have again a 2D lattice. You pick a point. Okay, you pick any point in the lattice and start drawing some connecting lines to the neighbors. So for example, if I pick this point, so this are all of its neighbors, not necessarily the nearest neighbors. So nearest neighbors are these two. Okay, this is farther than this distance. But whatever neighbors you see, let's try to connect this point to those neighbors. And then when I connect that, say if I connect this to this, I'm going to draw a perpendicular bisector of that. Okay, and I will repeat the same thing for all of its neighbors. So this perpendicular bisector, okay, connect to this, draw a perpendicular bisector, right? Which other point is left? This, and any other? So the two corners are still there. So this and this. Let me do. Okay. So let me go a step back. So this perpendicular bisector I would have drawn. Okay, I can draw that. No issue. So this and this. Draw a perpendicular bisector, this and this, draw a perpendicular bisector. Now look for an area which is enclosed by all of this, right? So all of this perpendicular bisector are enclosing this area. You see that? If I would have drawn this perpendicular bisector here, no issue in that, but that is farther from this enclosed area, so that will not count. In principle, you can do that. Okay, so the Wigner-Seitz cell will be this enclosed area. Connect to neighboring points, draw perpendicular bisectors. Find the smallest area that is enclosed by these lines, and that is your Wigner-Seitz cell. So it's a primitive cell. If you repeat this area, you will be able to generate the whole lattice. And how many lattice points does it have? How many lattice points are there? One. Just one, about which you have drawn it. I could have drawn the same thing about this. You can keep repeating it. Okay? Because it's a perpendicular bisector, so they will be non-overlapping. Now, if I have a point in this region, so that will be closer to this point than any other point. Say this point. It is closer to this point than any other lattice point. This point will be farther from all of those points and closer to this. Got it? Yes, if I pick a point here, so this is closer to these 2 points but farther from this. So this is not inside that region. Closer to that point, the given point, than any other point. So that is Wigner-Seitz cell. Now, it's just a geometrical representation of the Wigner-Seitz cell, but in the semiconductor physics, it has a huge importance. So later on, we are going to study the band structures, and there Wigner-Seitz cell is going to play a major role. There is something called Brillouin zone, and that depends on this Wigner-Seitz cell. Okay. So right now we are not at that stage, so we will just think about it geometrically, just in the form of a primitive cell. So this is about 2D. Any question in this? No? Okay, if no question, let's move and see what would happen in 3D. So 3D, of course, the shapes will be more complicated, but you can follow the same procedure. So you had perpendicular lines. Here you will have to draw perpendicular planes. So you pick a point, look around, and look at your neighbors. You connect to your neighbors and draw perpendicular planes. So if there is a point there, I will connect to that, and there will be a perpendicular bisector plane. And I will look around at all the points, and I will draw all of these perpendicular planes, and then I will look for this enclosed volume formed by all of these planes. So for BCC, this is how the Wigner-Seitz cell is going to look like. Do you understand? Yeah? Because at the center is a lattice point. You connect that lattice point to all of these neighbors, right? So if I connect this to this, so there is a plane, this that is going to bisect it. If I connect this point to this point, so this plane is going to bisect that, so you will get this football-like structure, okay, which is enclosed, truncated or octahedral. For FCC, it's even more complicated. This is for FCC, very weird shape. But the procedure remains the same. Okay, you keep connecting to the neighboring points, draw perpendicular bisectors. I have given on the next slide how we can draw this, so let me do it for you. So when we have these neighbors here, right? So this is the neighbor, this is the neighbor. I will draw perpendicular plane here, here, and then here, here, right? And then for this, and then for this. So you can keep doing that. You will be able to draw all of this perpendicular plane, and the enclosed volume will look something like this geometrically. Okay. So this was the Wigner-Seitz cell. Specifically, see, FCC we will not even talk about in this course, but this is important. This will come later on, okay, in the energy band diagram. So for silicon, this shape is important. So we have seen till now what is a lattice, what are primitive vectors, a primitive unit cell. So all of these are the quantities which can generate the whole lattice, right? But now we can understand that always these primitive vectors or the primitive cells may not be very convenient to work with. Yes, geometrically very good, you can generate every position vector, you know, good. Mathematically everything is fine, but we would like to work with some easier shapes, right, which are easier to work with, and they will still be able to generate the whole lattice but may not be exactly the same as the primitive. So the restrictions on the primitive cell is that it has to be the smallest one and it has to contain one lattice point. But sometimes it is not convenient. For example, in the FCC you saw that parallelly piped did not look convenient at all. Yes, I will be able to generate the whole volume through that, but it's very difficult to work with that. So what we do, we generate some convenient cells which we call unit cells. So primitive unit cell is the smallest volume unit cell, but unit cell is a more generic term we can use. So unit cell is a structure which you when repeat will be able to generate the whole lattice but may not contain exactly one lattice point. Okay, so unit cell or conventional unit cell is what we are going to talk about now. Okay, so for simple cubic, this is the unit cell. In the simple cubic case, unit cell or primitive unit cell, both are actually the same. For BCC, this thing is a unit cell. Okay. Primitive unit cell was different. You have seen what was the primitive unit cell, but this is a unit cell. And it has how many points? 2 points, not 1 point. But if you keep generating this thing, it will be able to generate the whole lattice without gaps. Similarly, for FCC, this is the unit cell, convention unit cell. So till now, we did not talk about the atoms. We only talked about the points. I always said it's an arrangement of points, geometrical arrangements of points, but in a material, there will be some atoms at those points, one atom or a group of atom. Okay, so I won't talk about the group of atom, but for our case, we will only be talking about mainly the silicon, germanium, elemental. So for those, we need not to talk about those group of atoms at every position, but only one atom will be sufficient. So now I'm going to put atoms on those points, right, and see what happens. So there is a lattice called diamond lattice structure. Okay, so if I put atoms at this type of unit cell, this is called diamond lattice. So what is this unit cell? You can see that there are atoms at the corner and it's a cube, right? A, and there are atoms at every corner. Okay, atoms at the face. Yes, this face, this face, this, right? This atom at every face. But there are some atoms inside also. So actually geometrically what it is, you can form a diamond lattice by interpenetrating two FCC lattices. How do you do that? So you have two FCC lattices. So there is a one FCC lattice. Okay, say this. Don't think about the atoms which are inside. So this is the FCC lattice. Now what you do, along the diagonal of that FCC lattice, you displace another FCC lattice by 1/4 of the diagonal. You won't be able to probably think about it right now. Go home and Google search or see the pictures. Okay, so what it is actually an FCC lattice, and I have this diagonal of the FCC lattice, and assume that there are another FCC lattice which is overlapping the first one, completely overlapping right now. Now I'm going to push that FCC lattice along the diagonal by 1/4. So I will be able to get this. So this is called diamond structure. Now we are going to look at it in a different way, right? It's a very complicated way to think that, oh, there are two interpenetrating FCC lattices. But I will tell you another way how to look at this arrangement of atoms. So there are some atoms at the face and the corner and some atoms inside, and this is called diamond lattice. And which elements have this type of arrangement? Carbon, which is the diamond, that's why the name diamond lattice, right? Silicon, that's why I'm talking about it. So it's going to be very important for us. And germanium. All of these have this type of lattice. The cube side is called lattice constant. The side of the unit cell is called lattice constant. Carbon has 3.57 angstrom. Just to give you some idea how small these are, 3.57 angstrom, 0.35 nanometer. For silicon, 5.43. Remember this number, will be very useful for you. 5.43 angstrom, or 0.5 nanometer, 0.54 nanometer, right? And germanium is similar, slightly larger. And of course, these atoms are going to form bonds. So these are bonds, covalent bonds, right? There will be covalent bonding. Silicon atoms will have covalent bonds. And what type of arrangement it is? So if I say look at this, what kind of structure it is forming? This. A tetrahedron, right? A tetrahedron, if you look at, so this. Okay, so let's now talk about the location of the atoms, right? It's very difficult to think in terms of two interpenetrating FCC lattices. So how do I find the location of these atoms, and what's an easier way to look at it? So what I'm going to do, I'm going to divide this FCC, the outer FCC lattice, into 8 cubes. I can do that, right? So this thing, I'm going to divide it into 8 smaller cubes. So I'm going to cut it like this. Okay, cut here, right, and like this. So you will get 8 cubes. Let me put this cube aside here, right? So this is one part of that cube which has an atom inside it. Okay, so that's this. And then I can look at the bottom half and the top half of this structure, right? So there will be cubes like this. So top half has 1, 2, 3, 4. Bottom will also have 4. Right? One, I don't know why this is not shown, but there should be 4. Okay. Now look at which of these cubes have an inside atom. So if I divide this in half and half, let me look at the bottom half first. So this corresponds to this. Yes, and then this is empty, the next one, and then there is another atom, this one. Okay, and when you go to the top, this has the atom, this empty, there is nothing here, and then this is this, and this is empty somewhere here. So inside atoms are in alternate cubes, right? Alternate. So this is filled, empty, and the top one will also be empty. See, this is the top one, corresponding to this will be the top, this is empty. So alternate cubes will have atoms. FCC plus alternate smaller cubes will have atoms. So that is your silicon. Can you find out, by the way, the location of these atoms? The coordinates. FCC is easier to do, right? The outer one. This, the outer structure, right? So the outer structure is simple cubic. If I even forget the face atom, so let's just talk about the coordinates of the corner atoms, right? So what will be the coordinates? These will be the coordinates. I haven't multiplied by the A. I have normalized with that lattice constant. So 0, 0, 0, say if this is say 0, right? So 0, 0, 0, right? 0, 0, 1. So you can generate this whole thing, all the corner points. Now the face points will have what? If I have to say draw the coordinates of the face points, what will it have? Half here, right? And 0 in this direction, right? So half, 0. So you can generate for every point, right? So they will have half, 0, half, 1, something like that. Right? If I talk about this point, so this will have 1 here, half here. Yeah. What about the inside points? This. So there are 4 atoms which are inside my unit cell. What about the coordinates of those? What about the coordinate of this point, say? This is the easier one. It's basically this. Yes? It's exactly in the middle of this small cube. So this thing is already a by 2. So half. And it's in the middle, so half of that. Half on this side, half on top. It's in the middle, right? Middle of that cube. So you go half. But half of half is 1 by 4. 1 by 4, 1 by 4, 1 by 4. So there will be several 1 by 4s, 3 by 4s here, right? So if it is this, so this will be 1 by 4. For an atom like this, so you have to go 3 by 4. So half and then 1 by 4. So you reach 3 by 4 then, right? So 3 by 4 here, 3 by 4 here, 1 by 4 here. So these will be the coordinates. You can find those out. This was the silicon lattice structure or the diamond lattice structure. Now, I also talked about compound semiconductors in the beginning. Now, some compound semiconductors, they have the same diamond structure. For example, gallium arsenide. But what will happen? Of course, because there are 2 types of atom, gallium and arsenic, so they will be located at, again, different positions. So that type of structure is called zinc blende structure. When you don't have one type of structure, but it's still like diamond like structure, so that's called zinc blende. For example, this gallium arsenide, right? So gallium atoms are inside, arsenic is forming this, the outer FCC. Okay, or you can look at it other way around also. Gallium is going to form the FCC and arsenic is inside. Both ways are possible. If you generate the whole lattice, you will be able to see it in both ways. So this is the gallium arsenide structure, very similar to diamond structure, but the location you see is different. By the way, I forgot to talk about this coordination number. So what is the coordination number? So coordination number is going to be 4 here. FCC had 12, but this is not FCC. These are 2 FCCs actually, interpenetrating. So coordination number here is 4. Why? Very easy to see. You know, what's the smallest distance of this point to other point? This, and this. That's it. All the other points are actually farther. So that's why coordination number is only 4. Now let's talk about the whole lattice again. Okay, we talked about the unit cell. Let's look at the big picture again. Let's talk about lattice planes. Why these planes are important? Because of the arrangement of these planes, in which direction I move, right? If I move perpendicular to this side, that side, it will decide my transport properties. If an electron is going like this, that direction, okay, it may have different conductivity. Okay, so that's why it's important to talk about different directions. Now, different directions will have different lattice planes, family of lattice planes. For example, in the same lattice, so you see the same lattice, I have repeated it 3 times, but I will generate 3 family of planes. You can see here. For example, this is one big plane, right? Another plane. So this is a family of planes which are all parallel to each other and equidistant. So distance between these planes are equal, right? But I can cut this lattice like this also. This. Okay, I can cut it like slanted also. This. Now, whether I move perpendicular to this or these, it matters. It matters a lot for an electron. It's anisotropic, right? Now, how do I mathematically characterize these family of planes, these set of planes? What is a mathematical, is there a mathematical way I can say that, okay, if I have this particular number, yeah, this is this family of plane, this number denotes this family of planes, right? So is there a mathematical way to represent this family of planes? So that way is Miller indices. So it's a way to uniquely describe a family of lattice planes. Now I'm just going to describe you the procedure, how to calculate the Miller indices, right? I won't go into the logic behind why this procedure looks like this. You can go and check, but we'll only talk about the steps involved, right? And that's enough for us. Okay, so how do I calculate the Miller indices and how does it represent a family of plane? Let's see. See, I have a plane which is intersecting my x, y, and z axis like this. So x-axis, it intersects at 3a. This side it intersects at 3b, and this side it intersects at 3c, 1c, right? So till now we talked about cubic lattices, so that's why a, b, and c were equal. But it can be different also, right? I mean, in a unit cell may not be a cube; it could be a cuboid, or it may have any other weird shape. So say this is 3a, this is 2b, and this is 1c, right? The spacing between the atoms might be different in different directions. Okay, so I know these intercepts. Now with the help of these intercepts, I can generate my Miller indices, and I'm assuming this is the origin. So identify the intercepts on the crystallographic axis. Crystallographic axis means x, y, and z. A, b, and c. So 3a, 3b, 1c. Now the second step is you divide them by the cell dimension, respective cell dimension. So if it is 3a, I'm just going to divide it by a, divided by b, and divided by c. Okay, so 3a, 2b, and 1c will become 3, 2, and 1. Divide by respective cell dimension. The third step is that you take reciprocal of these three. So it will become 1 by 3, 1 by 2, 1 by 1. Okay? And then you multiply each one of them with their denominators LCM, least common multiplier. Okay, or you can say least common denominator. So what will be the LCM of 3, 2 and 1? 6, right? So multiply with 6. Multiply with 6. 6 into 1 by 3, 6 into 1 by 2, 6 into 1 by 1. So you get 2, 3 and 6. So 2, 3 and 6 are my Miller indices. Okay, so that's the procedure. Simple. Take the intercepts, divide by their respective cell dimensions, take the reciprocal, multiply with the LCM. So Miller indices are denoted by H, K and L usually. So if I denote it in HKL form, okay, so I put a round bracket. So whenever I am doing anything with the round bracket, it means it's a plane expressed in the form of Miller indices. So 2, 3 and 6, instead of writing 2, 3, 6, we simply write 2, 3, 6 and put a round bracket there. So that represents one plane with Miller indices 2, 3 and 6. Okay. Now let me give you some other examples. So let's talk about this first. What will be the Miller indices of these? Calculate. It's a cubic lattice AAA and it has same intercepts. So what will be the Miller indices of this? Calculate. One, 1, 1. Yes. Intercept is going to be AAA divided by A. So that will be 1, 1, 1. Reciprocal of 1, 1, 1 is 1, 1, 1. There is nothing to multiply, right? I mean LCM is simply the same. So it's 1, 1, 1. So this type of plane is 1, 1, 1 plane. Then what about this? What about it? A. This is the intercept. What about this intercept? So this is going and not intersecting anywhere. It's going to infinity. So intercept is infinity. This is also. So this will be 1, infinity, infinity. Yes. Take the reciprocal, 1 by 1, 1 by infinity, 1 by infinity. So that gives you 1, 0. Okay. You don't have to take the LCM of this because there's an infinity involved, so you can just leave it here, 1, 0, 0. Okay, one more example. This. This is A here. A here. Intercept on A axis is A, intercept on this axis is also A. I'm assuming it's cubic. You can assume ABC also. What about the intercept on this C axis? There is no intercept, infinity. So A, infinity, right? So 1, 1, infinity. Take the reciprocal 1, 1, 0. Leave it here because you don't have to multiply with the LCM in this case. Okay, so Miller indices is 1, 1, 0. What if I have something like this? Let me talk about the plane first. This plane. The shaded one. What's the intercept on this? No intercept. It's not going to intersect. So infinity. Intercept on B. Minus B. Intercept on C. Infinity. Yeah. So infinity minus 1, infinity, right? In fractional intercepts. Take the reciprocal. So that will be 0, minus 1 and 0. Now in the Miller indices, minus is represented by a bar. So 0, 1 bar 0. Okay. Let's now again talk about the parallel planes, right? So this family of parallel planes, they all have one set of Miller indices. All of these planes will have one Miller indices. Okay. So that is 1, 0, 0 here. All of them will have 1, 0, 0. So 1, 0, 0 not only represent one plane, it represents a family of plane which is parallel to that plane. If you calculate the Miller indices of this also, you get the same thing. You can try that. Okay. For this, you will get the same also. Similarly, this will have the same set of Miller indices, which will be 0, 1, 0. This will have what? What will be the Miller indices of this? You can pick any plane and then calculate. Assume this is the origin, say. No, so this is this plane. So 0, 1, 1. Okay. Intercept is on this axis and this axis, but not on this axis. That's why 0, 1, 1. Infinity AA, so that will become 0, 1, 1. Got it? Similarly, so this family of planes, you represent them by the round bracket. So when I put a 0, 1, 1 with a round bracket, it means the whole family of planes I'm talking about. So this is equivalent plane. Now, what is an equivalent plane? All these three are equivalent planes. They are not parallel to each other, but they are still equivalent. Can you think why? Yes. Okay. So if I create a family of say 1, 0, 0 or 0, 1, 0 or 0, 0, 1, right? It's the same arrangement of atoms because of the crystal symmetry. So if my electron moves say in 1, 0, 0, 0, 1, 0 or 0, 0, 1, it's going to encounter the similar set of planes, similar arrangement of atoms. So as far as my electronic properties are concerned, it's the same thing. So why should I say they are different? So they are called equivalent planes. Although they have different Miller indices, but still electronically, material property wise, they are considered equivalent. 1, 0, 0, 0, 1, 0, 0, 0, 1, I will encounter similar planes. I go like this, or like this. But in which lattice? In a cubic lattice. In a simple cubic lattice, I'm saying, right? In a more complicated, I will have to see whether 1, 0, 0, 0, 1, 0 and 0, 0, 1 are same or not. Okay? So these equivalent planes, they are denoted by these curly brackets. So if I have a set of equivalent planes, I may choose any of them, say 0, 0, 1, 1, 0, 0 or 0, 1, 0. And if I put a curly bracket, say if I write this 0, 0, 1 with a curly bracket, so then not only it represents 0, 0, 1 family of planes, it represents all families of planes which are equivalent to 0, 0, 1. Got it? So which are the other set of planes which are equivalent to 0, 0, 1? 1, 0, 0, 0, 1, 0. So collectively it represents all of them if I put a curly bracket. So that's the nomenclature. Okay, so 0, 0, 1 set of planes or 1, 0, 0 set of planes or 0, 1, 0 set of planes, whichever way you like, you can write it. Okay, so lattice plane direction is basically, how do you determine the direction of a plane? It's determined by a normal through the plane, right? You put a perpendicular to the plane and that direction gives you the plane direction. Okay, so we say that this is the direction of the plane. So it's characterized by the normal. So vector component of a vector normal to the plane, and what that vector will be we will see, and they are denoted by square brackets. As Miller indices are denoted by curly brackets, they are denoted by square brackets. So how do we determine them? What's the procedure to calculate a lattice direction? So let's try to find a vector normal to the plane first. Okay, so let's say this is some vector L equal to x a cap plus y b cap plus z c cap. So a, b and c are your what? Primitive vectors, right? Primitive vectors of the lattice. And x, y and z can be some numbers, real numbers. Can be anything, integer, non-integer, not necessarily it has to be an integer. And so step 2 is that, so the components are x, y and z. Okay, if they are already least integers, right? You can't, so they are already integers and you can't take any factors common out of them. X, y, z are integers and you can't take any factors common out of them, then the direction is simply x, y, z with a square bracket. Okay, if they are say not integers or there are some factors that are common, right? So what you do, you first reduce them to the least integer. For example, either you multiply them with LCD, least common denominator, say they are in fractions, say 1 by 2, 2 by 3, 4 by 5. So take the LCD, least common denominator, and multiply with that, so that you are able to convert them into integers and they will be the least integers. Or you can also divide them by LCM. If you can take some factors say common, so just divide by the LCM to obtain this least integer form. We will see some examples. So for a cubic system, what do we have? This is the cubic system, right? Now what will be a vector, say, which is normal to this plane? Any vector which is normal to this plane. How do you represent that? So that vector can be represented by what? So this is along the A direction, and B and C direction the vector does not have any components, right? Only then the vector will be perpendicular to this, right? It does not have any component in B and C. It is along the A direction, so it will be some x will be something, but y and z will be 0. Yes? So it will be some x, 0, 0. If I say what are the vector components, x, 0, 0. Right? So it will be some x, 0, 0. Okay? Now, x can be any number. I can take this x out, and after clearing the fractions, the direction is going to be 1, 0, 0. Okay, so x can be any number, but if it is already 1, perfect. If it is not say 1, right, it is say 1 by 2. So what do? Multiply with the least common denominator. So you basically multiply by the 2, right? Because what is the least common denominator will be? 1 by 2, 0 by 1, 0 by 1. So 2, 1, 1. So that will give you 2 basically, and you multiply by the 2, so that fraction will get clear. 1 by 2 into 2 will become 1, times 0 you multiply with the 2, it is 0. Again this is 0, so that will become 1, 0, 0. Okay. Okay, so simple, right? So this direction is 1, 0, 0. Let's take another example. So similarly, these directions will be 0, 1, 0 and 0, 0, 1, right? Similar procedure. So the vector normal to this will have only this component, right? This will be 0, this will be 0. So say this is 0, y 0, and then you do the procedure, clear the fractions out. So this will become 0, 1, 0. Similarly, 0, 0, 1. So the second example let's take, which is a different example, it's a plane like this. So what will be a vector which will be normal to this? So something like this in this direction, which is perpendicular to this. So how do I represent that? It does not have C component, it has A and B component. So some x comma y comma 0, right? But we need to take perpendicular to this, so x and y must be equal. Otherwise that will take an angle. Say if x and y are not equal, so it can go here or it can go here, but because it is perfectly symmetric, this and this is equal, and if I want to go exactly perpendicular to this, so x and y must be equal. So that will be something like x 0. And if you clear out the fraction, so that will become 1 1 0, right? I mean, take the LCD or whatever LCM, so that becomes 1 1 0. So direction perpendicular to this will be 1 1 0. Okay. So interestingly, for a cubic system, the Miller indices and the direction, they are actually the same. I mean, you denote them in a different way. If you put a round bracket, so that becomes Miller indices. If you put square brackets, then that becomes direction, right? So for example, what is the Miller index of this plane? 1 0 0, right? And the direction is also 1 0 0. Similarly, 0 1 0. Miller index, and the direction is also 0 1 0. Similarly, what are the Miller indices of this plane? 1 1 0. Direction is also 1 1 0. But that only works for a cubic system, or you can say cuboid, right? If say this is not a cubic system, then this will not work. Okay, then the direction and Miller indices, they may not match. So just be careful, although we mostly will deal with the cubic system. Okay, so as we have seen that certain planes are equivalent, so certain directions are also equivalent, right? Say I move in 1 0 0 direction, 0 1 0 direction, or 0 0 1 direction, they are equivalent. When you won't see any different arrangement of atoms. So similarly, we can have a set of equivalent directions as well. For example, a family of equivalent directions, it's going to be denoted by some x, y, z, right? And that will be denoted by these angle brackets. Okay, if you are denoting the planes, curly bracket. If you are denoting directions, so these brackets. So for example, 0 0 1, 0 1 0, 1 0 0, 0 0 1 bar, it means 0 0, but 1 is negative. Doesn't matter, I move in this direction or exactly opposite direction. If it's like an infinite crystal, it's the same thing, right? I move in, say, this direction or the opposite direction, I will see the similar arrangement of atoms. So this is equivalent to this. So similarly, all these other directions also. So they can be combinedly written as 0 0 1, these brackets.